Hey guys, hey AP Physics, how are you guys doing? Um, I'm just gonna do some notes and some quick review, um, and we're gonna look at circular motion. And before we do that, though, let's go back and let's look at some free body diagrams because we're gonna have to draw free body diagrams, label all the forces. All right, so let's jump into this. So let's look at just a basic free body diagram. All right, we have a box. It's on a table, and let's say that this box is sliding to the right. And remember, we can write a velocity vector. We could just represent that that it's moving in that direction, and I'm going to put it up here. All right, so what's one of the forces? Definitely have the weight of it, or the force of gravity. So we got the force of gravity. Another force, we have the normal force. Normal force is pointing straight up because the normal force is the force that the surface is pushing on it. So if this is flat, the surface is pushing straight up. Okay, what other force? Well, we can say that there is, let's say that there is some friction here. So this is not a frictionless table. It has some friction. So here's my free body diagram. Note that it's moving to the right, but there is no force. Like a lot of people like say, oh, it's moving to the right. It must have an applied force. Well, that's not true. There doesn't have to be an applied force for it to be moving to the right. This could be an example of like you send a box, like you slide it, and it's just moving on its own. It's going to eventually come to a stop because it has the forces here. But it doesn't have to be an applied force. A baseball player sliding into second base. Um, there's no force pushing him. He's just sliding into that second base. So there's a force of friction. Um, so in this case, here are the forces for this scenario. Let's make it a little bit more complicated here. And let's say now we have this scenario where this thing is sliding, but we're trying to slide it up this ramp here. So we have this velocity. It's going up the ramp. So let's label. If it's going up the ramp, we got friction going down. Now here's the weight. Weight always goes straight down towards the center of the earth. The earth is pulling you down, so you got your weight going down, your force of gravity going down. Now here's the tricky part, and a lot of people get this mixed up. A lot of people would do something like this. This is a common mistake. Like, oh, we got the weight going down, so the normal force is going up. But this is not right. The normal force is the force of the surface pushing on the object. So the surface is at an angle. So the normal force is at an angle. So the normal force is always perpendicular to the surface. You see how here these two lines are perpendicular. Same thing here. This is perpendicular. And normal actually means perpendicular. So that's where we come up with the word normal force. So it's perpendicular to the surface. Okay, so we have this frictional force here. Let's just do a quick recap of friction. What the equation for the frictional force is. Now, we have two different, this is pretty general because we have two different types of, this is the coefficient of friction. We have static and we have kinetic. In this case, we're going to have, like, it's definitely going to be kinetic because it's moving. So here is our frictional force. We have this set up. Well, in this case, the normal force is pretty easy because the normal force, it's not flying up off the table or it's not going down below the table. So these two things have to be equal. So in this case, we have our normal force is just mg. So there's our frictional force, our coefficient times our weight. And remember that coefficient just says like how rough that surface is. So it depends on the actual materials. Okay, let's come over here now. I'll do this in black. So now this is a little bit trickier. So let's give this an angle. All right, let's give that an angle. So now we have our frictional force. So we still have our frictional force is equal to mu times my normal force. And we can, again, this is the kinetic coefficient. So the normal force, so here, it's not mg. See how like here the normal force is mg. But here the normal force, it's not mg. What it is we have to put that angle on there. So I'm gonna put a little, let's get a little space here. I'm gonna erase this. We know this is mg. But I'm gonna put on here this line right here. And if this is an angle right here, there's a little bit of trick can be done to show that that is also that angle. So this is an angle. All right, so these two angles are the same. So if we look at this, the normal force here is only this component. So I'm going to draw the component in red here. It's only this component. So that component is, go back to black, is have to use a trig function here. And so that is mg, because this is mg. And then here, this is my adjacent side. So I'm going to use cosine of theta. Okay, so there's a little recap of friction. Friction's kind of hard. So we got some free body diagrams and some friction. Now let's get into more of the circular motion. Okay, so where do I want to go from here? I guess we can recap let's say that you have something and it's going around in a circle. Maybe you're swinging something around in a circle, or maybe it's a record player. Well, we have, if we have objects on here, like let's put an object right here. And we'll say that this is a coin on a turntable. That's a really common physics problem. Here's the center, and we're going to give this a radius here. We're going to give it an r. Okay, so this object right here, let's say it's spinning around this direction. Well, if it's spinning around in this direction, it has two types of speeds. It has an angular speed, and it has a translational speed. So it's moving. So you can think of this one right here. What would happen if this turntable would just disappear? Well, if the turntable disappeared or all the friction left, you could think of this object would be moving in that direction. So the velocity is in that direction. And I actually don't have to draw the velocity. It's not a force. So I can put the velocity vector and just put it over here. So I'm going to say the velocity vector, it's going to go off straight off in a straight line. So there's the velocity vector. So let's relate these two. Remember my angular velocity is delta theta over delta t. How many revolutions or rads that I go in a certain amount of time. And to relate this, well, the tangential velocity, if you go farther out, think about that. If you're on a merry-go-round or something, the farther out you are, the faster you're going to go. So the relationship there is the farther out, the bigger the r, the more velocity you have. The angular velocity stays the same no matter where you're at here. If you're here, or you're here, or you're here, the angular velocity stays the same. You're always going the same amount of radians in the same amount of time. Like this guy, let's say it takes 2 seconds to go around, takes 2 seconds for this guy, takes 2 seconds for this guy. It doesn't matter where you're at, it takes 2 seconds. And they're all going 2 pi. They're all going 2 pi. So you can see how the angular velocities here are all the same. Okay. So let's get into the circular motion. So that was just a quick review. Now let's give a scenario here of a roller coaster, and it's on the top of a part of the roller coaster, and we're gonna say that this is circular. So to get circular motion for our cases, we have to make it the ideal like circle to figure this out. All right, so this has like a certain radius. Like you can see how like if this was a circle, everywhere along here would have that same radius. So it's a circle. And another thing that you're gonna hear a lot is that this is moving at a constant circular motion. So if this thing's moving around at a constant circular motion. Okay, so we have this radius. Let's draw the free body diagram here. So let's draw the free body diagram. So let's say that that this cart right here, well, if you're on a roller coaster, you're gonna make it over that top of the hill. So you have a certain velocity here. All right, so you have a velocity. Now let's draw the free body diagram. Well, you have the weight going down. Like I think that's the easiest one to draw. You always have that like weight pulling you down. And then you're also on a surface. So this surface is going to be pushing up on the roller coaster car. So it's pushing up. And notice I'm going to draw this a little bit less than mg, and we're going to talk about that. So here we got this thing going around, and it has these two forces on here. Again, the common mistake here is you think like, oh, it's got a velocity this direction. It must have something like an applied force here. But that is not right. So it doesn't have to. Could have like a little rocket pack on it or something, but it doesn't. Like roller coasters, you just set it in motion and then they start going. So there is no applied force. These are the only two forces. All right. So something we need to review again for centripetal motion is we have this equation, v squared over r. The acceleration is equal to v squared over r. And it has a good derivation to it, but we won't focus on that right now. So we have here is the acceleration. Now one thing that for centripetal motion, acceleration is always, this means center and like center seeking. Okay, so centripetal, this is center seeking. So that means that the acceleration here, and I'll draw the acceleration in green. So the acceleration is going to be going straight towards the center. The acceleration is going like at this point, it's straight towards the center seeking. All right, so if this is my acceleration, well, remember F equals ma. So centripetal acceleration, or sorry, centripetal force is mass times centripetal acceleration. So in this case, let's look at this. Let's analyze this. So I'm going to sum my forces. Let's say I want to like find out what that normal force is. Well, I can sum my forces and I can set it equal to mass times acceleration. But in this case, it's centripetal acceleration. All right, so what forces do we have? Well, we have mg going down. So we'll call it down negative because you guys are used to that. So we have minus mg. Well, if mg is negative, the normal force is opposite. So we're going to have positive Fn. Sorry about my dog. Okay, so we have the positive Fn, and now here is something that's tricky. This acceleration, that's going down too. It's going in the same direction as this mg. So we have negative centripetal acceleration. Okay, so here let's analyze. Let's say that we are using this. We're trying to find this Fn. But let's bring this mg over to this side. So I'm going to add mg to both sides. And I have this subtraction here. And instead of AC, here I'm going to use v squared over r. So there's my normal force. So is the normal force equal to mg? Well, only if it was just, if it wasn't moving. If it wasn't moving, it could just be sitting there, then the normal force would equal to mg. But you can see as the velocity increases, that normal force drops because this right here would increase. There's another way you can make the normal force drop, and that's if you decrease the radius. So let's say you have a really small radius here. Well, you can think of, you're going to feel weightless here. You're going to feel like your normal force is really small because you're going around this, doing this drop really quick. So you can think of like, oh, the normal force is like it's like you're like dropping off of this. So I don't know if you can picture this, but there's two ways you can decrease that normal force, and that's by going faster or making that a tighter turn. So you can make that radius smaller. All right, I think that's a lot of information. There is one more thing that I want to just put up for you because we haven't reviewed this. But let's look real quickly about the gravitational force. Okay, you might say like, oh, gravitational force, that's just Fg is equal to your weight. Well, what causes your weight? And that is like a fundamental force, that's gravity. So what causes this weight? We have to be more specific. And we have to say like, oh, here is the equation. What causes your weight? Well, that's because you have two masses. Any two masses are going to have a force pulling it together. In this case, we have huge mass of the Earth, and you have your little tiny mass. I mean, this is like really not to scale. Got forces act in pairs. But these are the two masses here that are causing this force. Let's look at these two. Let's say that we have the same masses. Well, these two things are going to pull each other together. And here's Newton came up with this equation for the force of gravity. And this is classical. So this is Newton's like classical theory. Now we have like modern theory. So just remember that this isn't like this is just a good approximation of how the world works. But with modern physics, we can talk about what Einstein figured out, what gravity is. But this is a good description of like how gravity works. So it works on the large scale. So here, if I were to find out what this force is, I would just use this equation. And my radius here, that is the separation distance. That's how far apart they are. And then the last thing, you might say like, oh, what's this big old G right here? Well, big old G is it's the gravitational constant. It's a gravitational constant. Um, and it's just something that you put in there to make these things equal to each other. And one little like note on that, the gravitational constant is actually really, really small. Because the the gravitational force is also really small. You might think like, wait a minute, it's huge, like you fall to the earth, you can break a leg. But that's because the mass of the earth is gigantic. It's huge. But over here, if you had two, let's say you had two, um, you know, golf balls and you put them up in space, well, that force of gravity is going to pull it together, but it's going to be a really small force. It's going to take a long time for those two golf balls to come together and meet. Okay, so I hope this was really informative and that this helped you. This is just a quick review. So let's start doing some problems. All right, good job, you guys.